Well, in the portion of gravitation, we are going to discuss the concept of satellite, how exactly the satellite works, what is basically a satellite, and how it operates, how satellite is made to reach the space that is out of the gravitational pull of Earth. So when we use the term satellite, we are referring to any body which is moving around another body. One of the body is fixed and another body is moving about that body. For example, moon is moving around the earth. So moon is a natural satellite of earth. Similarly, if any other object is moving just on the circumference of the earth, then that body will be known as satellite. So satellite can be natural or satellite can be artificial. So whatever body we fire from the earth, that is supposed to be an artificial satellite. And in the natural system or in the universe, there are many examples like sun, like moon is orbiting around the earth. So moon will behave like a natural satellite. Similarly, uh, for planet Jupiter or for planet that is Saturn, we find that there are a lot of moons. In one case, 12 moons are there or 9 moons are there. So the moons are basically the natural satellites of those planets. So celestial bodies, when we use this term celestial, means which are in the universe, that are in the outer solar system or in the outer space. So celestial bodies revolving around the gravitational field of the planet is called satellite. So every planet has got a gravitational field, and any celestial body which is moving about that planet or moving around that planet, that is what known as satellite. Satellites will be of two types. Number one will be the natural satellites. Moon is a satellite of Earth, and artificial satellite. They are launched by man, such as the name of the satellites will be Rohini and Aryabhata, etc. They are artificial satellites. That is, these satellites are put into the space with the help of a rocket. So there can be a one-stage rocket, a two-stage rocket, or a three-stage rocket. So rocket accommodates the fuel, which is a liquid fuel, and satellite is on the top portion of that particular uh, that is rocket. So when the rocket is fired by remote, we find that the gases comes out and gradually it attains very high speed, and when it reaches to the space, then the final rocket will be burned off and the satellite or that body will be put into the space that is called artificial satellite. Now these artificial satellites are generally launched by man, and satellite of mass m. Now we have got various concepts like satellite is launched in such a way that it is just reaching in the outer space, but it is just moving near the circumference of the earth. In that case, the radius of earth and the radius in which the satellite is moving will be the same. So satellite of mass m revolves in a circular orbit with radius r around the earth. The necessary centripetal force needed for the circular motion is provided by the gravitational force of earth. Like for example, if earth is moving around the sun, then gravitational force between sun and earth will provide the centripetal force to earth so that earth can revolve around the sun. The same is the case with the satellite. So the centripetal force needed for the circular motion is provided by gravitational force of earth to that particular satellite. So between satellite and the center of earth, there is a gravitational pull. That gravitational pull provides necessary centripetal force to the satellite so that it can revolve just on the circumference or just touching the circumference. So in that case, what we'll do, we'll use the formula of the gravitational force. Normally the formula is Gmm over r square. But here the mass of Earth we are taking is me. So the formula must be Gme m over r square, where G is the gravitational constant and its value is 6.67 10 to the power minus 11 mgas units, and me stands for the mass of Earth, and small m, that stands for the mass of satellite moving around the Earth, and the distance of that satellite from the center of Earth is supposed to be r. And in the right hand equation we have written mv square over r. As a whole, this function is centripetal force. M is the mass of satellite and r is the distance of satellite from the center, and v is the orbital velocity. So from both sides, if we cancel off m and we cancel off r, we will get the formula for the orbital velocity. So in that case, v square will become gme over r, and if we want to find v, then we take the square root, and that will become orbital velocity of that satellite around the Earth. If the distance is equal to the radius of Earth, then we take capital R instead of small r. Now, our assumptions are me is the mass of Earth, v is the orbital velocity of satellite, r is the radius of satellite's orbit. And if satellite is existing at height h from the circumference, then total distance of the satellite from the center will be Re plus h, and that is orbital radius. Re stands for radius of Earth. Normally we take radius as 6400 kilometers. So now Re plus h is the distance of the satellite from the center, that is Re plus h. Re stands for the radius of Earth, h stands for the height of satellite above the Earth's surface. So the net distance will be Re plus h from the center. G is acceleration due to gravity on the surface of Earth. But if we wanted to find the acceleration due to gravity at height h from the circumference, then we have not to take only radius of the Earth, but we have to add height in that radius, and the net distance of the satellite from the center will become Re plus h. So we have to find acceleration due to gravity at that height, and that is supposed to be g dash. So g is supposed to be on the circumference of the Earth, and g dash, if we write, it will be at a specific height from the circumference. Now we come towards the orbital velocity. In order to understand the orbital velocity, first of all, we must know what is the time period. So, if satellite is orbiting around the Earth just on the circumference, then its time period is taken as distance over speed, and distance is obviously circular, so it should be 2 pi r, where r will be the radius divided by velocity, and t is the time period of satellite, that is time taken by satellite to complete one revolution. So orbital velocity is generally given by function gm over r under root. But if that small r is the radius of Earth, then we make our formula gm over re square root. But if the satellite is at height h from the center, then we add radius of Earth to that height, and the net formula will become v is equal to gme over Re plus h under root. And if we modify this formula by equating with the me square over r, then our net combination or the net formula will become gre square over Re plus h. So orbital velocity can be calculated mainly for gm over r under root, or it is gme over re under root, or at height h it should be gme over re plus h, and that can be written as gre square over re plus h under root. Now from this expression, that is ge square over re plus h, it is clear that orbital velocity does not depend upon the mass, because mass is not involved in this particular, in the final formula. So now in the given figure, what we are finding that m is the mass of the satellite, p is the position of satellite on the circumference, and a tangent is drawn. So at p, the tangent drawn will represent the velocity of the satellite, and r small is the radius or the distance of the satellite from center of Earth. But the radius of Earth is taken as RE. So if P is at height h from the circumference, then net distance from center to P will be RE plus h. So small r is the distance. Small r is the distance right from center to P, and this small r is nothing but Re plus h. So r can be replaced in many cases by Re plus h. M is the mass of the Earth and it is concentrated at the center. Wherever small m is written, that is the mass of the satellite. It depends upon the height of the satellite above the Earth's surface h. Greater the height of the satellite, smaller is the orbital velocity because it is an inverse relation. And the third concept is if a satellite is very close to the Earth, it means it is just touching the circumference, then h will be very, very small as compared to Re. Re stands for radius of Earth. In that case, He will be neglected, only be taken into consideration Re or simply R. Re means radius of Earth, or R also stands for the radius of Earth. So in that case, h will be negligible as compared to r, and then orbital speed of the satellite is given by. Now the orbital speed will be v is equal to g me over r square root. This is what earlier I have explained you. Or if it is height h, then r plus h will be taken. But now, if we find that h is neglected, then the formula will become v is equal to under root g me over r. And this can be calculated in terms of acceleration due to gravity and radius. So whatever r is in the denominator in the main expression, we will multiply and divide by r, and then we come to the conclusion that v can be written as under root gr. Now we put the value of g and put the value of r, and then we will get our result in meters per second. So if meters are converted by dividing with 1000, it will become kilometers. So we will find that orbital velocity of the satellite just around the surface of Earth, that will be equal to 7.92 kilometers per second, which is approximately 8 kilometers per second. Therefore, if a satellite is moving just on the circumference, in 1 second, it will cover approximately 8 kilometers of the curve.